So another useful coordinate system is called polar coordinates, or special case cylindrical coordinates. So in polar coordinates, we no longer have our axis moving along with the particle again. So this is going back to being more similar to our Cartesian coordinates, except instead of having our coordinate system fixed in space, they're going to, I guess, track that particle. So the position vector is going to be moving with respect to r and theta. And r is just the distance from the origin, and theta is a rotation from some reference direction. So if we have our particle's path here and a particle motion, we can define our position vector and that's r, and that's going to have some magnitude r, so a distance from the origin, and that's going to be acting in the radial direction. So we call this direction our radial direction. And this is our circumferential direction. And that is u theta. And our position vector is the vector r. This is just r that isn't a vector, the scalar value is the distance of the particle from some origin. So the radial direction always extends directly outwards from the origin, passing through wherever that particle is at that moment in time. And then the theta direction is measured counterclockwise from the horizontal, from that radial direction. So UR always extends outwards. From the origin. And then U theta is always measured counterclockwise from the horizontal. Always measured counterclockwise from the horizontal. So our position vector is just that. It is the vector that represents the magnitude or the distance from the origin of the particle, and it is along our vector UR. So if we think about this is a very common coordinate system to use when we're talking about robotic manipulation. We have maybe some arm. We know how much that arm is extended outwards from some pivot point, and we know how much it's rotated from some reference angle. So when we want to calculate velocity, the instantaneous velocity is still the time rate of change of our position. So we can write our velocity vector is equal to our position vector dr dt, which is equal to the derivative of r ur dt. So in this case, our position vector, that r is going to be changing. So if I go back up here, at some other moment in time, our particle has moved here. Our coordinate system, our new r is going to be here. And our u theta will be over here. So they're moving with the particle, and so UR is changing with respect to time, as well as that magnitude R. So we have to use the product rule in our derivative, and we end up with R dot, so the rate of change of the distance of the particle, times UR plus R times UR dot. So what is UR dot? UR dot is the time rate of change, and we can use the same method we used to calculate our the rate of change of our tangential unit direction vector when we did n and t coordinates. And we can say u dot r is just the time derivative of ur, which is equal to dur d theta. It's just related to that change in angle d theta. And we use chain rule d theta dt. And then we can also prove that dur d theta is equal to u theta. So finally, we can write u dot r is actually equal to theta dot, which is d theta dt, times dur d theta, which is equal to u theta. So lastly, we can write our velocity vector as r dot times ur plus r times theta dot u theta. Let's go back to blue. So this is the vector form of our velocity. So it has two components. The r dot is called the radial component, and the r theta dot is called the transverse component. The speed of the particle at any given instant is the sum of the squares of these components. So if we want to find the total velocity, the magnitude of velocity, or the speed, we would just do the same thing as before for finding the absolute value, and it would be r theta dot squared plus r dot squared. So think about the values that are in this equation. If we have a problem where we are calculating, or we are given information about the distance of something from some fixed point, some origin, like the distance directly measured, so r, then we might be looking at, or it might be easier to use polar coordinates. And likewise, if we have some information about the rotation, theta, we need to know how fast something is spinning, then again, maybe polar coordinates would be more important to use. So all we did here to calculate this velocity vector is we wrote down our definition. We defined our coordinates, r and theta. We defined our position vector, and then we took the time derivative of that, which got us this. We did some geometric manipulation, which you don't have to worry about too much, but we ended up with this equation down here in blue. And this is the important equation. Our velocity vector is equal to the time rate of change of the distance from the origin times our radial unit vector plus r, the distance, times the theta dot, the rate of rotation about that origin, times our u theta. So yeah, in this case, maybe to make this a little more clear, r dot is just equal to dr dt, it's a scalar. And theta dot is equal to d theta dt, and it's also a scalar. So how is this sitting? Is this Is this comfortable? Are we ready to move on to acceleration, or does this need to just sit in for a bit? I think these types of problems become a lot more, they make a lot more sense when we see some examples and you can understand what kinds of problems this would apply to. So if we're moderately comfortable with that, and let's attempt acceleration, which is always fun. So acceleration, instantaneous acceleration is the time rate of change of our velocity. So let's start with that. We already know where this is going. And we have our definition of our velocity. We just wrote it above. So we have d dt, this big beautiful equation r dot ur plus r theta dot u theta. So if we use the same process again, we're going to end up with ur dots and u theta dots, and we want to write those just in terms of our coordinate directions. We don't want to have time rates of change of our unit vectors. So we can find those in terms of our components, things that we know, which is r and theta. And if we do some manipulation, you can read the textbook that has the derivation in here. It's very similar to velocity, but what we end up with is a radial component of acceleration, which is r double dot minus r theta dot squared. And that is times our ur, plus our transverse component, r theta double dot plus 2 r dot theta dot. And this is times u theta. So this is our equation for acceleration. I mean, the derivation is not too long, but you will end up here, and this is our equation of motion, or one of our equation of motion. So when we think of polar coordinates, whether it's cylindrical or polar, this is just in 2 dimensions. So this would be like cylindrical and polar are the same. Cylindrical would just be a 3rd dimension where you're adding a z component, and then the acceleration of motion in that z direction, or that z component direction, we could use our equations of motion for rectilinear straight line motion. But for now, let's just think about 2D. We have our equation for velocity and acceleration. Questions where they're going to give you information about r and theta should be immediate flags that, oh, we should be using polar problems or polar coordinates. So then lastly, if we just wanted to find the magnitude of our acceleration, this would just be equal to sum of the squares of the components, all to the square root. So r double dot minus r theta dot squared plus r theta double dot plus 2 r dot theta dot squared. All right. So that's polar coordinates in 2 dimensions. If we want to look in 3 dimensions,
a second, go back up a second, please.
Gonna go back up, yeah.
Okay. Okay, thanks, I'm good.
Perfect. So in 3 dimensions, we can call these cylindrical coordinates if we defined our coordinate system very much the same way as we did before, where instead now we have our position vector is now going to some path that's in 3-dimensional space. And our position vector now has components RP, and that's equal to R UR plus Z UZ. If we take the time derivatives and we go through all of our steps again, we can get our position VP is equal to R dot UR plus R theta dot U theta plus Z dot UZ. We can see the motion in the Z direction is just everything that's in front of that UZ direction vector, and that's pretty, it's the exact same as our motion for rectilinear motion. And then lastly, our acceleration is equal to R double dot minus R theta dot squared UR plus R theta double dot plus 2R dot theta dot U theta plus Z double dot U theta. So if we just look at the beginning terms over here, this side is the same as 2D. When we're adding the 3D term, we're just adding those Z components. So if we have information about the Z position, the Z velocity, or Z acceleration, it just adds to the previous equations just like this.